Excellent. This is indeed the location of the thick ascending limb. Let me cut it out for you using the microscope, as it is a delicate operation. All right, we have now cut the relevant piece of renal tubule for our experiment. You can look at the resulting section on the microscope screen. Now insert pipettes into both ends of the tubule by clicking on the micromanipulators. Watch the 2D animation on the screen to understand the flow of perfluorescate. Raise the lab pad when you are done. Are you done watching the animation? What we are going to measure is the volume of reabsorbed fluid through the tubule. In short, we will perfuse one end of the tubule with the perfluorescate saline, and measure the resulting volume collected at the other end. The difference will tell us how much volume the perfluorescate has lost while traveling through the tubule due to being reabsorbed by the epithelial walls. In theory, we can calculate the volume reabsorbed through the walls of the tubule using the following formula: volume reabsorbed equals volume entering the tubule minus volume leaving the tubule. We will measure the volume of fluid leaving through the sides of the perfused tubule, theoretically being reabsorbed in the body, during the time it takes for 1 nanoliter of fluid to accumulate in the collection pipette. In real life, the collection pipette is filled with a light red dyed oil, so it will be easy to see the meniscus marking the division between the oil and the perfused saline coming out of the tubule. Click on the bottle of tritium methoxyinulin to learn more about the perfluorescate. The saline entering the tubule will contain tritium methoxyinulin. Methoxyinulin is a plant-derived non-metabolizable sugar that is not transported by animal epithelia, so it will remain in the perfused fluid, and will not be reabsorbed. It has been made radioactive by combining it with tritium, which means that its concentration can be measured easily in very small concentrations. This way, by measuring the radioactivity of the perfluorescate in the collection tube, we can measure the concentration of methoxyinulin and thus deduce the amount of volume reabsorbed by the tubule. Set up a syringe with our saline solution to start our reabsorption experiment. Pick a syringe full of saline and set it up on the microscope. I have now injected the saline with radioactive methoxyinulin into the tubule using the micromanipulators. Once 1 nanoliter of perfluorescate has been accumulated in the collection pipette, you will need to remove the pipette to measure the concentration of methoxyinulin. Remove the collecting pipette from the microscope and add a rubber bulb. Now you can transfer the perfluorescate to the vial on the workbench. Bring the vial to the analytical workbench. To measure radioactivity, we first need to mix our perfluorescate with a scintillation cocktail, which includes scintillator molecules. The radioactivity emitted by the methoxyinulin in the perfluorescate will excite those scintillators, which will in turn re-emit photons we can detect. Holding the vial, add the scintillation cocktail mix using the re-pipetter. These photons from the scintillator molecules can be counted using a liquid scintillation counter. The data provides us with an indirect measurement of the radioactivity, and thus the concentration of methoxyinulin in our perfluorescate sample. Place the vial in the scintillation counter. Now start measuring the radioactivity by pressing the Start button. Great! We have now measured the radioactivity of our perfluorescate sample. This will be our control in the absence of drug X. Let's use our radioactivity data to calculate the amount of fluid reabsorbed by the renal tubule. Look at the screens to the left of the workbench. We are going to fill in this table for the control experiment. Use the formulae to calculate the flow rate of perfluorescate in the tubule and the amount of fluid reabsorbed. The collected fluid that exited the tubule had 2,000 counts per minute of methoxyinulin. Using the formulae on the screen and the calculator, what was the flow rate of the perfluorescate into the tubule and the amount of fluid reabsorbed? That's right. The entering flow rate of perfluorescate inside the tubule was twice the rate at which it was collected in the collection tube, which means half of the perfluorescate was reabsorbed through the walls of the tubule. Now, let's see if the process of reabsorption is active. It could just be that the fluid is leaking out of the tubule via a rip or a bad seal between the pipette and the tubule, or the methoxyinulin is being concentrated by an osmotic effect. For example, the osmotic pressure in the bathing saline might be higher than in the perfluorescate saline, triggering water to leave the tubule through simple diffusion. If the reabsorption process is indeed passive and due to higher osmotic pressure in the external saline, what would be your prediction for the volume reabsorbed in the absence of oxygen to make ATP? Good job. If the reabsorption is driven by passive processes such as osmotic pressure, the volume of reabsorbed fluid should be the same in the presence or absence of oxygen. Here are the results when the tubule is deprived of oxygen. V out equals 2 and C out equals 1000. So V in equals 2 times 1000 divided by 1000 equals 2 and R equals 2 minus 2 equals 0. So, with no oxygen present, no fluid is reabsorbed, which suggests that the reabsorption is active. It also means we still have work to do to uncover the full mode of action of drug X. Here is a model for the ion transport process in the thick ascending limb of the nephron, based on prior research and experiments. Have a look around to learn about the different processes and where drug X could be interfering. As you can see, there are many possible sites of action for drug X. It may not even target any of these known sites. It seems the first thing we have to do is to check if drug X affects reabsorption when applied to either the apical or basolateral side. We'll perfuse using the exact same saline, but include drug X in either the perfluorescate or bathing saline. I will run the experiments by changing the saline myself to save some time. Okay, I have run the experiments and measured the concentrations of methoxyinulin in the perfluorescate after applying drug X in the perfluorescate or in the bathing saline. I have updated the table on the screen on the analytical workbench. Now your job is to finish filling this table with your calculations. Fill the equation on the screen to calculate the reabsorbed fluid rate for the basolateral side. Indeed, as you might have noticed, our experimental values were similar to our negative control without drug X, and we logically deduced the same V in and reabsorbed fluid rate R. Fill the equation on the screen to calculate the reabsorbed fluid rate for the apical side. Well done. We can see a difference here, with a reduced reabsorbed fluid rate. Great. Now the table is complete. I will leave it up for you to make your own conclusions. What findings can you draw from these data? Great, we are starting to narrow things down. On the apical side, it looks like drug X could potentially block ion reabsorption either by inhibiting sodium reabsorption via the paracellular route, or by blocking the sodium